Good afternoon. As some of you may have heard me comment, I didn't expect a lot of people in here. I thought that you would all be sick to the back teeth of uncertainty after, 25 years of it being in the standard, and of people looking at it, thinking about it, trying to get out of it, working out when it applies and when it doesn't. So thank you all for coming. And I'm not going to talk about how to do uncertainty. So if you're expecting slides full of equations and models, then I've disappointed you already, and I apologise for that. But there are much better people to explain how to do uncertainty than NATA staff. And I strongly advise you to look at the courses that NMI offers. They're very good, and you'll get a lot more out of those working through. What I want to talk about is why you should want to do uncertainty for your quantitative methods, regardless of the standard. You would have seen the I am going all over social media. Well, we're all here now, so thank you. So the standard says that you must do uncertainty. But how does that actually benefit you when you do it? Just to be clear as well, we're talking about the uncertainty of a measurement. We're not measuring uncertainty. So it's measurement of the uncertainty of the measurement, not the other way around. They're quite different. And we're talking about quantitative measurements. We're not talking about qualitatives, go, no go, presence, absence, fail, pass. We're talking about things where your test results in a numerical measurement, a number. So all quality systems, whether it's a 17,000, 15,000, 9,001, Lean, Six Sigma, they all have common goals. And the aim is to create a quality framework that ensures that an organisation's outputs are traceable, repeatable, reproducible, which is not the same as repeatable, reliable, predictable, credible, and sensible. By sensible, well, you know, it rhymed with all the rest, but what we mean is fit for purpose. So all quality systems are designed to support those outcomes. They provide a structure within which any organisation should be able to produce repeatable, reliable, predictable output, whether that's widgets off a production line or test results out of a laboratory. And for that reason, everything that is in the standard is there for a purpose to support those outcomes for organisations. They're not just put in there because someone thinks that the lead assessor is going to get bored and needs to check some other stuff that the lab could be doing. It actually has a purpose. I keep knocking that, I'm sorry. We all know that at labs, customers need to know the measurement uncertainty in order to make acceptance decisions when the result is close to a spec or a tolerance or a cut-off of some sort. And you all know that 17025 requires it under 7.6. But measurement uncertainty is where the rubber really hits the road for a quality system. It's where the technical work comes up together with the quality system to give you a quantifiable measure of the quality of a measurement. It's evidence that you've got the method under sound technical control, that you have followed the method, you've controlled all of the components, and you understand the method well enough to have a valid uncertainty. You can have all of the procedures, policies, work instructions, training modules that you like, but you still have to be able to execute the method correctly. For example, you can give me the best written method for producing a souffle that was ever written in the history of soufflés. Put me in the best kitchen and give me all the right equipment, and I guarantee it's going to fail because I am just not competent to do that. And the same can happen with your testing. It's not enough to have the procedure. It's not enough just to send the stuff to calibrate. You've got to make sure that your staff are competent, that they know what they do and that they understand the method. And it comes out in the uncertainty. We all know that perfect measurements don't exist. You can never know with absolute certainty what the true measurement of the measurand is. All you will ever know is that you've got 1 point in a probability cloud of potential true measurements. And that's why there is always that probability. Within a 95% confidence interval, you think your value is probably in this range. Don't forget about that other 5% that can come to bite you with decision rules. Please think carefully about decision rules. So, how is measurement uncertainty a measurement of the quality of a measurement? Quality is never achieved by accident. And a guy by the name of Philip Crosby, who is quite a well-known quality systems person, was quoted as saying that. Edwards Deming, the grandfather of quality, said that you can't test quality in the final product. It must be built into the process. The same is true of your test result, and measurement uncertainty is a measure of how well you have built quality into that test result. Measurement uncertainty takes all of the components of the method in use and distills all of the individual uncertainties into a single number attributable to the result. We all know that technically, measurement uncertainty is a property of the result, not a property of the method. But if you remember note 2 in the standard, it allows you to apply the uncertainty to all of the method if you've got it under control. So we tend to work on it from that point of view. If you're in calibration, you have to do it every time, of course. If all of the individual contributing factors are optimised, then the uncertainty is going to be as large as it must be to include 95% of the potential true values, and as small as it's possible to get when you've got everything under technical control. And that brings you to the question, now that you've got your uncertainty, is it realistic? And to work out whether you've got a realistic uncertainty, you need to do a reality check. You need some mechanism of working out whether this is the kind of uncertainty that is reasonable. Do other facilities doing similar tests on equivalent matrices, do they get an uncertainty like this? Your reality check can come from a range of sources. If you're doing bottom-up uncertainty, you know, where you do the mathematical model, you sit down and you do it on paper, then if it's possible, try a top-down, a repeatability or reproducibility data-based measurement uncertainty. It's not always possible to do top-down. If you've got a test where you are destroying the test article, you're not going to be able to do that twice. if you've got a test where you cannot replicate the sample, you're not going to be able to get repeatability data. There are a couple of other kinds of tests that fall into that range, but leaving those as exceptions, if you've done it by bottom up, do a reproducibility data set and look at the uncertainty you get from a top-down estimate. They're not going to be the same. It's not possible for them to be the same unless you've done something weird with the numbers. But they should not be significantly different. There should be a large area of overlap between your bottom-up and your top-down uncertainties. They should show that the way that you calculated was reasonable. Another way that you can do a reality check on your MU is through comparison testing. The commonest comparison testing around the place, of course, is proficiency testing, but that's not the only method of comparison testing you can do. If you're doing proficiency testing, you really hope that your PT provider, or if it's not an accredited PT, then whoever set it up, is going to provide the uncertainties with all of the participants' de-identified results. Because that lets you see what everyone else doing your method on exactly the same test article got for their uncertainty. And you can see if yours is okay. I have seen PT data sets where 80% of the results fall very neatly in a very tight range, and the other 20% are crazy. Someone getting 100th, 1 in 100 smaller than everyone else, and someone else getting 10 times bigger an uncertainty. And the sad thing is the Z scores were okay, so no one looked at the damned uncertainty. You should be looking at where your uncertainty sits compared with your peers doing the same test on the same test article. Because if you have got an uncertainty 1/10 of everyone else, or 1/100th, God help us, of everyone else's, the commonest reason that I hear for that is that they're just a whole lot better than everyone else at doing the test. And I'm sorry, I don't believe it. Paint me cynical, but that's just not how these things work. Why is your uncertainty so small? If you did a bottom-up modelling, the chances are you don't actually understand the method as well as you think you did, and you've missed out a major source or two of uncertainty. And you need to go back to your calculations and find what was missing. Another common reason for getting very small uncertainties is that it's been calculated from repeatability data on idealised specimens using the best equipment in one sitting by one scientist on one day. And so what you're seeing is optimised near perfect uncertainty from repeatability data. But that has no bearing on what happens to normal client samples. And so it's unrealistic. It might be something that you would like your staff to sort of aspire to have similar uncertainties to each other, but that's not an uncertainty you should be publishing. And you should be thinking about changing the way you calculate that to use reproducibility data, which is between people, between days, possibly between laboratories. I want to mention as well, if you can be participating in a very small group comparison study. So there are some tests around where there are simply not enough numbers to justify a large-scale proficiency testing scheme. And the PT providers are not going to go out of their way if there's only 2 labs in the country doing a specific method. So if you find yourself in the position where your comparison testing is with one other lab, for whatever reason, and you discover that you've got different uncertainties, significantly different uncertainties that do not overlap, you've got some serious thinking to do. Because if you two are the only ones doing this work and your uncertainties are significantly different, no one is ever going to be able to compare your results. And that's the whole purpose of the whole traceability thing, so that you can compare results that have been gained using the same method that we've accredited, so we've said you're doing it right. You have to be able to compare those. So if you are in a small group and you're going to do a comparison study, well, the standard says you've got to have your acceptance criteria determined before you do the test. Because as you all know, we don't decide what passes after we've done the test. We do it first. And part of that discussion is going to be what you expect from the uncertainty. And usually you're going to say that you expect that both results are going to fall within an uncertainty that is, of a similar quantum, and you might add some things around how tight the repeatability in the study is going to be. But uncertainty is really going to help you when you're doing very small numbers. And it might be obvious, but I'm going to say it anyway because it comes up, I'd say, once every 6 months or so, that a lab is doing a very small comparison study, and there's only 2 or 3 labs, and there's only 3 data points, and their acceptance criteria is that we're going to say it's passed if the values are within plus or minus 2 standard deviations of the mean. Can anyone see the problem with that? Anyone at all? Because if you've only got 3 data points, in fact, if you've got anything less than 6, it is mathematically impossible to ever have an outlier. So please don't send that one through because you'll just make me cry and we'll say no. I was asked once where it said that you couldn't do that in the criteria. And my response was that I'm not going to start putting mathematical proofs into criteria. So when you think about acceptance criteria for those kind of small group comparison studies, just think it all the way through and don't go for things that are impossible to be an outlier. There are statistical tests that you can apply for very small numbers, but I'll let you Google those. Please Google them, don't chat them. You'll get some weird responses because I don't think ChatGPT has actually learnt about stats yet. So how is good technical control demonstrated by measurement uncertainty? Good technical control means that all of the components of the method are optimised and the method can produce in a predictable, reliable, repeatable, blah, blah, blah manner results ongoing, not just as a one-off. It shows that the staff who've got competency records for the method are actually competent to do it, and that those who are authorised to perform the test can do it within the specs that you put around it in your lab. And it shows that the people who are reviewing results to authorise reports to go out understand the method. Because if you don't understand the method, you're not going to have good uncertainty. If you are making people authorised, able, in the old speak, you're making them signatories, not NATA signatories, we don't have those anymore, but people who are authorised to issue reports that are NATA endorsed. You need to be confident that they really understand what they're looking at. There was a case in Victoria a few years ago using some pretty flash new kit that made an understandable error in retrospect. It identified an organism as an exotic biosecurity threat when it was in fact a normal commensal cross-reacting, just something that we have in the soil in Western Victoria. And it was not in fact a biosecurity threatening organism that closed down an entire farm and put people into quarantine. And the person who authorised the result didn't know that the library that was being compared for that test was not based on Australian organisms. They didn't know the cross-reactivities that were possible with Australian organisms in that area. And they really were not, whilst they were a very competent person in a lot of ways, they were really not up to issuing reports for this kind of work. Slightly different area because it's not got uncertainty with it, but I like to remind people about that one. It gets too easy with new equipment to just follow the prompts and do what you're told by the equipment. You need to understand what's going on. Uncertainty pushes you to understand what's going on with your test. Your uncertainty, if it is showing good technical control, has to be defensibly valid. So you've got to be able to say, we calculated it this way from repeatability data instead of reproducibility data for these reasons. You need to understand how you did it and why. It has to be reasonably recent. If you're going to claim that you don't need to do uncertainty because you did it 10 years ago, I've got some questions about that. Have you really not changed your equipment in 10 years? Do you not have any new staff? Has the standard method not been revised in 10 years? That's possible, I get, but there are other things going on in your lab that are going to change what your uncertainty is. And there is no period that is required for you to repeat uncertainty, but you're supposed to repeat it when you need to. And if you've changed over all of your staff in that 10-year period, then whoever was doing it originally is long gone. You need to think about it again. So reasonably recent is one of those plastic how long is a piece of string things. And we all like to think that new versions of the standard will improve the method and therefore improve the uncertainties you're going to get. Not always true, but we'd like to think that. It can show you that you've got consistency between your staff. There's no requirement for you to know what your individual staff repeatability and uncertainty is, but when you're thinking about, are they competent? How good are they? It's not an unreasonable thing to ask them to do 10 replicates and do the uncertainty as a top-down and have a decision made about what you want the uncertainty for a given method in your lab to be. It's demonstrating that you are keeping everyone repeatable, reproducible within your lab. And if you've got more than one site, MU can help you to demonstrate that you've got sound technical control across all of your sites. And that is particularly important when you've got a multi-site arrangement and we may not be witnessing at every one of your sites every year. How else might you use it? As I said, you might be using it to confirm competency. You might use it as part of your continuing QAA for infrequently performed tests. Maybe annually you're going to collect some reproducibility data, get half a dozen of your staff to do 2 each, put that data together and see if you can still get the uncertainty in the same range that it was a year ago. You can use uncertainty to help you with infrequently performed tests. When you are implementing new equipment, has your uncertainty changed? Is the new equipment and the way you are using it as good as what you were doing, hopefully better than what you were doing with the previous one? And you may be using it to try and improve your method control, make changes to the method, change the pipette you're using, the balance, those individual components. Altogether, truly understanding the uncertainty of your methods puts you in control, and it minimises the risk to you as a business, as well as the risks for your customers trying to make decisions based on your results. But it gives you more confidence in your business and your staff. If you've been doing measurement uncertainty just because we ask you to at 7.6, I hope I've given you some insights into why else you might want to do it. And I strongly encourage you to do it not for us, but for you, because this is just another clause in the standard that is there to support sound testing. Thank you very much.
What is uncertainty limit?
Uncertainty is a property of a result because we can never know the true value of a result. So the uncertainty is the range within which we can expect the true result to sit. And it's usually reported at 95%. You can report it at 99.7 if you want to go to 3 standard deviations, just for something to do. But uncertainty is about the fact that you can't know what the true value is, ever. Whether you're using the steel rule from the CMT guys out the front to measure something, or a laser, or a dressmaker's tape measure, you can never know what the true value is. And the uncertainty quantifies that lack of knowledge.
Thank you, Di. Please join me in thanking Di for that session. Thank you.